Okay. Okay. All right. So today I'm going to present the construction and classification theory of non-compact orientable surfaces. And this will be a basic talk, I mean introductory level. And just I will not go through the proof. Rather, I will say in and around what's the proof and what's the idea is kind. And the main references I already mentioned in the abstract section. It is the paper of Ian Richard. So I'll mostly consider these two statements. I mean, the Ian Richard, I think my screen is also visible. Yeah, Ian Richard representation theorem. So it says that there every surface has a suitable form. I mean, well, nice, good form. And you can, if you are given any surface, then you can find a copy inside this well-organized class. That okay, use the color, this class. Okay. And the second thing is the Kare-Kharto classification theorem. It says that if you are given any two non-compact surfaces, then you can find out three invariants. Based on these three invariants, you can say whether they are homeomorphic or not. All right, so here is our introduction section. Okay, so throughout this talk, I'll assume all surfaces and border surfaces. Just note that surface means is a two manifold without boundary. And when I write a border surface, it means two manifold with non-empty boundary. Okay. And I will always assume surface is connected. Surface is connected. It is, you can drop this assumption connectedness, just you need to consider component wise. And you can also drop this assumption, orientability. Yeah, there are a classification theory for non-orientable surfaces also, but today I will not consider all these non-orientable surfaces. Just because one fact that let's write on a different color, every orientable surface can be embeddable in R3. I mean, you can see every orientable surfaces, and most non-orientable surface or surface or border surface, border or unbordered surface cannot be embeddable in R3. So most non-orientable surface or border surface, you can't see it. We'll see that most orientable surface can be embeddable in R3. Why it is? Okay, so here is a basic question. I mean, you can think it as a motivational question or something. Suppose you are given any two non-compact surface. How do you decide whether they are same or not up to homeomorphism? I mean, how do you distinguish them? For example, first one, consider the M punctured plane and N punctured plane. Okay, just one question. Is it enough zoom, or do I need to make it larger something? Or you can see the words, or it is enough?
Yeah, it's okay.
Yeah, then it is fine. Okay. So M punctured plane and N punctured plane, where M and N are positive integers. So delete M points from the plane and delete N points from the plane. So you can see some basic algebra. You can use the basic algebraic topology from here. So like let's say I deleted M punctured x1, let's say xn, xm many points, and you know that this is homotopy equivalent to wedge of I equals to 1. Okay, n circles, or where it is I'm using M, so it would be. So M punctured plane is homotopy equivalent to the wedge of M circles. So in particular, its fundamental group is Z star M times. It's a free group. Okay, and N punctured plane, you can find out that it is N times Z, right? And now you can check that using basic group theory that M equals to N, then they are isomorphic. Okay, and so what's the conclusion? Conclusion is that if M equals to N, then you can say that they are homomorphic, but if M not equals to N, then they are not homomorphic. And what is the main point? You are checking the cardinality of the puncture set. You are just checking the cardinality of puncture set and you are deciding whether they are homeomorphic or not. So what about the next one? So here I am deleting a full interval from sphere. So sphere means it is a 1-point compactification of R2. I am thinking as, okay. So R2 disjoint union infinity is equals to S2. Okay. So, and as close 0-1 interval sitting inside S2, I'm thinking. What is? So are they homeomorphic or not? Okay, you may construct some homeomorphism, explicit homeomorphism sub formula, then you can show that they are homomorphic. But today I will show that they are homomorphic without writing any equation. I mean, implicitly I will say that I will produce some homeomorphism, this kind of thing. And the third one is that I'm considering the Cantor set, standard Cantor set, middle closed, middle 1/3 interval delete, middle 1/3 delete, so on. So first surface is that delete Cantor set from the x-axis, and second surface is that delete Cantor set from the x-axis again from the y-axis. So again you can apply your guess here. So here I am deleting uncountably many points. This here, uncountably many points. And again here I am deleting uncountably many points. But here 2 times uncountable, more or less, roughly is the idea. More or less, I'm deleting 2 times uncountable set. So you can guess that, yeah, they are homeomorphic again, because 2 times uncountable is again uncountable like this. Well, so this is the rough idea. But if it is your idea, then what about this one? So here my x can be, let's delete it. Yeah. So here x can be this set. Okay. Or x can be this set. First surface produced from deleting x from the x-axis, and the second surface is produced from using deleting a copy from x-axis, again a copy from y-axis. Well, so at the end, so notice that in both cases we are deleting countably many points. X cross 0 is a countable set. Again, x cross 0 union 0 cross is again countable set. So you can check that, you can say that, I mean, guess at least that we are deleting countably many times, and 2 times countable is countable. But the point is, when x equals to this one, these two surfaces are not homeomorphic. But when x equals to this one, then these two surfaces are homeomorphic. We'll see at the end. Okay, and the last question, last motivational question, here is 2 surfaces. Here are 2 surfaces, you can see it. The one surface is the red one, so it is called the Loch Ness monster surface, and another surface is the blue one, it is called the Jacob ladder surface. So here you can again apply your guess. So your guess, you can guess that the first surface, I mean, this one has exactly one end. So roughly an end means how, I mean, you can go towards infinity using only this direction, I mean the right direction, but you can go towards the right side or left side, I mean, you can say plus infinity or minus infinity like this. So the blue one has exactly 2 ends, you can roughly say, or the red one has exactly one end. So if they were homeomorphic, then the number of ends would be same, but here they are exactly one end, and here 2 ends. So this is the rough idea. Okay, we will see at the end of this lecture that why they are not homeomorphic. So they are not homeomorphic. Sorry, this is a bad notation. This is, yeah, they are not homeomorphic. Well, so let's recall some background. So it is the construction and classification theorem of border and compact border surfaces. Okay. All right. So let G be a non-negative integer. So of course G is finite, just mentioning, and SG be the compact borders or compact surface obtained by adding G many handles to the sphere. So what is the meaning of adding handle? So if you want to add a handle, you just take a sphere, okay, delete a small interior of a small ball, delete interior of a closed ball, and then add one hole torus. So what is the meaning of one hole torus? This copy. So it has exactly one boundary. You have to glue this boundary with this boundary, right? Similarly, here I'm doing here. So here is the sphere with no handles. So it is means S0. Here I have so here I considered one handle exactly. So I delete a interior of a closed ball, then I add one handle. So handle means a one hole torus. So it is one hole torus. Sorry. Okay, so I add one hole torus here. So here I delete two. So here I consider two pairwise disjoint closed balls. Then I remove their interiors. Then I add two handles. So it is S2. It is S1. So it is torus. Okay. Similarly here, so it is S3. I consider three pairwise disjoint balls, remove their interiors, then I add three one hole torus along the boundaries. So so it is the meaning of adding handles roughly. You can make it precise. I'm not going to define it. What is the meaning of adding handles? It is just a quotient pace, like adding. Yeah, this is kind of quotient pace after identifying this boundary with this boundary, or here two boundaries like. Okay, so so what are all what are all compact surfaces? So recall that I assume surface means without boundary. So the class construction theorem says that if you are given a compact surface, so it is homomorphic to some SG. So as I mentioned here, so SG, S0 is this one, S1 is this one, S2 is, so for some G, it is homomorphic. So X is homomorphic to some SG. All right, so this is the construction theorem. And the second theorem is the classification theorems. If you are given two compact surfaces, how do you distinguish them? So this theorem says that if you are given SG and you know SG equals to SH, if and only if G equals to H. So number of handles actually completely determine a compact surface. And this number is called genus of the surface. Genus of the compact surface. So if you are given a compact surface, you just need to know number of handles of this surface. That is enough to that is enough to determine this surface up to homeomorphism. Well, so what about the compact border surface? So first I'm defined here. So G be a non-negative integer and B be a positive integer. All right. And SGB is nothing but take a genus G surface. Let's draw it first. For example, let's draw genus 2 surface. Okay. And I remove the interior of two pairwise disjoint closed ball. So I deleted two, or maybe let's say another ball here. So I removed their interiors. So I just removed here the interiors, pairwise disjoint closed balls. Okay. So this surface is nothing but S2, 3. Okay. So construction theorem says that if you are given a compact border surface, then it is homeomorphic to SGB for some G and for some B. This is more or less follows from the closed surface construction theorem. You just, so suppose you are given a compact border surface. You know that abstractly it is a compact surface, means its boundary also compact. So X is compact means del X, because del X is the closed subset of X, is compact. And del X is a one manifold without boundary. So del X consists of, let's say, S1, wedge, S1, wedge, S1, finitely many, right? So X has, so roughly X has finitely many holes. You have to fill up these holes by disk. Once you fill up this hole by disk, then the resultant surface is actually closed surface. Now you have to use the construction theorem of closed surface. That is the idea. And the classification theory says that if you are given any two compact border surface, Then you just need to know number of number of handles, I mean the genus G, and number of boundary components. These two invariants are the enough to determine a compact border surface up to homeomorphism. All right, so here is the G, B, and H. Okay, and so this are enough. These things are enough to. Okay, so let's move on. So what you just notice here that I am considering every time finitely many handles. No number of handles is exactly the finite. It may be 0, it may be 1, 2, 3, but it can't be infinite. So if I want to add infinitely many handles to a surface, how do I do then? So here is a notion of accumulating a puncture by handles. All right, so the first one. Okay, so let's P be a point belongs to sphere. Okay, so P is in the picture, P is here. P is this puncture. Okay, so I deleted this point. And now consider countably infinitely many. You can't consider uncountably many pairwise disjoint closed balls. Countably many because surface is second countable. Okay, so pairwise disjoint collection of closed balls and remove their interiors. So I have removed here the interiors. This interior removed, this interior removed, this interior removed, so on. Okay. So you just need to ensure that every neighborhood of P, every neighborhood of this puncture contains all but finitely many this. So this is the neighborhood of U, neighborhood of P, and this neighborhood contains all but finitely many this ball. Okay. Now I add torus, one whole torus along this boundary, right? So on. If you add this after as a resultant surface, you find that this puncture is this is the point not on the surface. Okay, so this process is called the puncture P is accumulated by handles, or there exists a sequence of handles converging to that puncture. Well, so you just notice that I am deleting a puncture. I consider a sequence of balls converging to that puncture. I remove their interiors remove their interiors of these closed balls. Then I added one whole torus along boundaries. This is the idea. But why I am considering only puncture point, not an ordinary point? Ordinary point means a point which is on the surface. Well, so if you want to accumulate an ordinary point by handles, then you just need to consider, suppose this is a point and this is a neighborhood, and you just need to consider small balls like these types of. Okay, so then you need to remove their interiors, then you need to remove their then you need to add handles, one whole torus. But notice that this point is on the surface. This point is on the surface. This is not a puncture point. Okay, this is not a puncture point, it is an ordinary point. But the resultant won't be a surface. Why? Because every surface is locally Euclidean. If you remove these types of ball, then every neighborhood of then there doesn't exist any neighborhood which looks like R2, right? So there is no notion of accumulating an ordinary point by handles, but there is a notion of accumulating a puncture by handles. All right, so let's move on. And here is the presentation and classification theorem. Okay, so presentation theorem says that any non-compact surface up to homeomorphism is of the form. First, delete a non-empty. This non-empty is crucial because if you you'll see it closed and totally disconnected. These two terms are not obvious why I am considering only closed and totally disconnected, but this term is more or less obvious. First, you need to delete a set, closed, totally disconnected set from the sphere. Then you have to add handles so that a point of a sphere is accumulated by handles if and only if it is a point of puncture set. Just as I defined previously, that there is only a notion of adding handles so that any sequence of handles converts to a puncture. There is no notion of accumulating an ordinary point by handles. All right. So here is the picture, I mean, illustration of, okay, you just notice that here. I deleted 4 points, puncture 1, puncture 2, puncture 3, puncture 4. Okay. I accumulated this puncture 4 by handles. So there is a sequence converging to this puncture. I accumulated this puncture by handles again. So there is a sequence of handle converging to this puncture. But this puncture is not accumulated by handles, and this puncture is not accumulated by handles, right? Okay, so notice that one thing here, that any neighborhood of this puncture, how does it look like? It contains infinitely many one-hole torus, and you know that one-hole torus can't be embeddable in R2. One-hole torus, let's write in short. S1, 1, G stands for first one stands for genus, and next one stands for boundary, can't be embeddable in plane. Okay, so any neighborhood of this puncture contains infinitely many one-hole torus. So in particular, any neighborhood of this puncture can't be embeddable in plane. So these types of puncture is called non-planar puncture. Okay. Similarly, this puncture is called non-planar puncture. All right. But look at this puncture. There exists a neighborhood of this puncture which does look like puncture disk, right? 0 less than mod z less or equals to 1, right? This puncture. So this type of puncture is called planar puncture. I mean, there exists a neighborhood which can be embeddable in plane. This neighborhood can be embeddable in plane. So up to homeomorphism, you just need to delete a closed totally disconnected subset or non-empty subset from the sphere, then you have to add handles. This will give all surfaces. You will see why I'm considering closed one and totally disconnected, these two words at the end. And here is our classification theory. Oh, I have already discussed this question. Idea of discarding accumulating a point, ordinary point by handles. I have already discussed it. So, okay, so let us define this notation, epsilon NP. So NP stands for non-planar. All those points which are accumulated by handles. So like this one. This is a handle, and sorry, this is a puncture accumulated by handles. This is another puncture accumulated by handles. So this surface has exactly 2 non-planar puncture and exactly 2 planar puncture. Okay, so here is the classification theory. So classification theory says that suppose you are given 2 surfaces, sigma 1 and sigma 2, and corresponding puncture set are given by this. This is the puncture set, non-empty, closed, totally disconnected subset of H2. Okay, so classification theory says that these 2 surfaces are homeomorphic if the number of handles, so number of handles is equals to number of handles is called genus. So number of handles of sigma 1 is same as the number of handles of sigma 2, and there exists a homeomorphism from puncture set to puncture set, sending the non-planar puncture set to the non-planar puncture set. This is the classification theory, roughly. Well, so it is a paraphrased version. This is, sorry, cancel. Oh, right. So it is not the exact version. I'll at the end, I'll consider the exact version of the classification theory. It is kind of short version or deformed version of classification theory. Well, so one thing that I want to mention, you can check it from here, that set of all non-planar, let's write here, uh, sorry, NP is a closed subset of this thing. This is just basic fact. You can check like a set of all limits point. How do you check set of all limits point is the closed subset? Because it is a closed set. This kind of idea you have to use to check that this is a closed subset of this thing. So the classification theory says that you are sending puncture set to the puncture set, also the non-planar puncture set to the non-planar puncture set. Now we are ready to answer question number 1 and question number 4. Okay, let's move on. So here is the question number 1. Question number 1 says that an M punctured plane and N punctured plane. So we are deleting M points from the plane, and M plus 1 points from the sphere. N punctured plane, we are deleting N plus 1 points from the sphere. So they are homeomorphic if and only if there exists a bijection between their puncture set. And puncture set is here, cardinality of the puncture set is just the M plus 1 and N plus 1. And there will be a bijective correspondence if and only if M equals to N, sorry. So this answers the first question. And the fourth one is this. Fourth one is this one. So let's erase this and consider this. Okay. So when X equals to, let's first consider this set 1 upon N union 0. Okay. So you can check very easily that X is homeomorphic to X cross 0 union 0 cross X. It is just here I'm just drawing. So sequence of X is here. Let's say draw like this one, this one, this one, this one, small one, and another sequence of this one. Okay, here is sequence, and so X is homeomorphic to this thing just because it has this subset has exactly one limit point, which is nothing but 0 cross 0, and it has exactly one limit point, which is 0. And other points are discrete points and they are countable in numbers. So you can just construct a direct homeomorphism, right? So once you consider the direct homeomorphism, you can just use the classification theory. So notice that this surface has no genus, I mean 0 genus, better say. And this surface again has no genus, right? So you don't need to consider non-planar puncture, because non-planar for a non-planar puncture you would at least need at least one handle. More concretely, we need countably many handles. Since there is no genus or no handles, so we don't need to check the number of handles. So it is basically 0, and it is also basically 0. So these two surfaces, when X equals to 1 upon N, this surface, so H to this surface homeomorphic to this surface. But when X equals to this one, let's say this one, they are not homeomorphic, because notice that when I draw here, so it is 1 here, and here small, 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 and here 1 here is small, small, small. So yeah, so let us delete it. I have to delete 1 upon N. Okay. All right. And delete this also. Okay. So now you notice that X cross 0 union 0 cross X. It has two limit points. One is located at here, another is located at here. So two limit points are, let's say, right, 1, 0 and 0, 1. In case X equals to this thing. And but X cross 0, it has exactly one limit point, which is nothing but 1, 0. So X won't be homeomorphic to this one. So classification theory, using classification theory, we can again say when X equals to this one, they are not homeomorphic. Okay, so now move into answer. Okay, now. Okay, so here is the characterization theorem of Cantor set. So notice that I first deleted So while considering all surfaces, I mean constructing all surfaces, I delete a set which is like this. It is a non-empty. So right, better. Epsilon is non-empty, closed, and totally disconnected. Totally disconnected means every component path, every connected component is singleton. Totally disconnected, right? So Brouwer characterization theorem says that a set is homeomorphic to the standard Cantor set if and only if it is non-empty, perfect. Perfect means each point is a limit point, compact, and totally disconnected, and metrizable. Metrizable means its topology comes from some metric, right? Standard Cantor set, you know how to construct it. So any space which is homeomorphic to the standard Cantor space is called the Cantor space. Okay. And the second one is that every compact, totally disconnected metric space, I just omit this notion, perfect and non-empty. Every compact, totally disconnected metric space is homeomorphic to a closed subset of the Cantor set. All right. So here we are now able to answer, here we can answer this question number 3. So question number 3, just to recall what you have asked in question number 3. So question number 3 is that delete Cantor set from x-axis and delete Cantor set x-axis union y-axis. Right? This was our question number 3. Okay. But notice that this thing, sorry, yeah, this one is also non-empty, perfect, not compact, totally disconnected, and metrizable. C cross 0 and 0 cross C. So using the Brouwer characterization theorem, we can say that 0 cross C union C cross 0 is homeomorphic to C. All right. And it has no genus, 0 genus, G equals to 0 and G equals to 0. Right. Now use the classification theorem. So classification theorem says that so number of handles is the same as the same number of handles. So we don't need to check because here genus is actually 0. Second one, we just need to check that there is a homeomorphism sending this set to this set, sending non-planar ends to non-planar ends. But non-planar ends is here empty set because we have no handles. For non-planar ends, we just accumulate handles, right? So this is vacuously true. This portion is vacuously true. Now, and there exists a homeomorphism just using Brouwer characterization theorem. So these two surfaces are homeomorphic. All right. So here is another question that I am going to discuss. So notice one thing that while deleting this set, let illustrate. Yeah, this set. This is a non-empty, closed, totally disconnected, metrizable, whatever, everything, right? So in particular, this set can be uncountable, right? It can be Cantor set, but I am considering only countably many handles. Let us move into the characters. Sorry. Yeah, here. At most countably many handles. All right. And I am deleting uncount. So deleted puncture set can be uncountable, but the number of handles is countable. So why I am not considering uncountably many handles? So the idea is if you want to add uncountably many handles, then you need to delete. Then you need to at first consider uncountably many pairwise disjoint closed balls. That is impossible, right? Because we are considering second countable space. All right. And so there is no notion of adding uncountably many handles. There can be at most countably many handles. You can say this other language like this. Let's say, okay. So this is kind of tricky. Alternative way of answering why not uncountably many handles. Alternative way. So I'm just why saying why it is possible. Suppose you are given a surface, right? It is abstract surface, it has a smooth structure. So a smooth structure gives you handle structure. Using handle structure, you can construct a compact exhaustion. What is the meaning of compact exhaustion? Compact exhaustion means you can consider compact border surface S1, S2, S3, so on, such that union of Sn is equals to sigma, and Sn is contained in interior of Sn plus 1, and Si is compact border subsurface. All right. And we know from the classification or construction theorem of compact border surface that each compact border surface can have finitely many handles. So what is the meaning of roughly what is then? We are taking countable union of handles, countable union of handles, and each Sn has finitely many handles. So countable union of finite sets roughly. So countable union of finite sets roughly it is countable. So this is the rough idea of why sigma, I mean any non-compact surface can't have uncountable many handles. Well, so the next question that one can ask, that if I delete Cantor set, which is uncountable, and I want to accumulate each puncture point by handles, but we have only finite at most countable many handles, but the number of puncture point is uncountable. Then how do I accumulate each puncture by handles? Okay, so the idea of this thing, so I'm considering this question. Let us erase it. Okay. All right. So how do I accumulate each puncture? So one line answer. Consider a countable dense subset of sigma, sorry, epsilon, and let's say subset is D, denoted by D, and accumulate each point of D by handles. That's right. Because I'm considering countable, dense subset, other points will be automatically accumulated by handles. Well, so let us illustrate this idea. Okay, so here is a picture. So this surface is obtained from deleting. So first I'll construct, okay. So this is the inductive procedure of constructing S2 minus Cantor set. How do I start? I start with the disk. So this is the disk. Then I consider a pair of pants. All right. It has two boundary comps. So pair of pants means this surface, compact border surface. S0 stands for zeros, 3 stands for number of boundary components. So here is a pair of pants. Then it has two boundary components. I add another pair of pants here, another pair of pants here. Again, binary pattern. Pair of pants here, pair of pants here, pair of pants here, pair of pants here. So you have to continue. It's a binary pattern. So the limiting surface will be S2 minus Cantor set. Okay, it is not easy to visualize from here why the limiting surface is S2 minus Cantor set, but roughly I can say Cantor set is obtained from deleting middle 1/3. So you can roughly think that middle 1/3 located at here, middle 1/3 located at here, middle 1/3. I'm just not considering this middle portion. And this is the left portion, right portion, left portion, right portion, this kind of thing. But yeah, it is not easy to visualize why S2 minus Cantor set does look like this. Okay, now I want to accumulate Okay, so I deleted. So this is a Cantor set. So let's Cantor set, and I deleted H2 minus Cantor set. So this one is this. Now I want to accumulate each puncture point, I mean each point of the Cantor set by handles. So I add handles here. So here is a handle. Here is another handle. Here is another handle. Here is another handle. Handle. Yeah. This way. So keep continue with this. So in this way, you can see that each puncture point will be accumulated by handles. But notice that I am using only countably many handles at most. So exactly countably many handles. So what is the set theoretic idea? My logic behind this, set theoretic logic behind this is that 2 to the power aleph naught is equals to cardinality. So we are considering binary pattern here. Binary pattern here. So 2 is stands for binary, and since we are considering inductive procedure, we are adding this pair of bands countably many times, and this binary pattern says that actually we can, at the end we are accumulating each puncture by handles. Well, at the end, I'll go to this procedure. This procedure roughly says that so this procedure, it has a name. It's called Goldman inductive procedure. I'll come to the point at the end of this talk. Okay, and so where I am deleting Cantor set or Cantor space, it is immaterial because of the classification theorem. Any two Cantor spaces are homeomorphic, right? So classification theory says that. So where I am deleting the Cantor space is not needed. I mean, not important. Rather, just we need to know that what are the puncture sets. So from here, you can just notice that the three invariants that I told in abstract section are the genus. Let us write. The first invariant is the genus. Second invariant is the puncture set. Third invariant is the NP. All right. And okay. Okay, I'll write this. Okay. So the next question is that, so how do you check? Suppose you are given an abstract subset, and you want to check that what is the suitable representation for your abstract surface. I have already told you how to consider, I mean, the representation theorem meaning is. So how do you check that your given surface has a representation of this format? I mean, how Ian Richard solved this problem, right? I mean, how he showed that every surface has a homeomorphic copy after deleting a totally disconnected closed subset, then accumulating each puncture point by handles. All right, so here is the rough idea. I'll not go through the proof, but I'll say what is the main idea behind the Ian Richard theory. So theory is based on space of ends. Space of ends. Okay, so an end means, roughly an end means a way to go towards infinity, and space of ends is the all possible ways to go towards infinity with some topology. That is why I'm writing space here. Okay. All right, so let us consider a definition. The first definition. So from now on, every circle will be assumed as abstract surface. We don't know whether it has a suitable representation or not, because I'm going to sketch a proof of Ian Richard classification theory. Sorry, construction theory or representation theory, whatever you call it. So a boundary component is a nested sequence, decreasing nested sequence. So P1, P2, so on, such that each Pn is open connected. Closure of Pn is non-compact. Boundary of each Pn is compact. Boundary means just set topological boundary. And for any compact surface, Pn is actually eventually doesn't intersect with A. So here is the picture or illustration. So P1 is the left portion of that this circle. P2 is the left portion of this circle. P3 is the left portion of this circle. P4 so on, right? And so you can check it easily that P1 is open connected. Closure of this is non-compact. Boundary is exactly the circle. So boundary is compact, and given any non-compact surface, given any compact closure subset, it is eventually doesn't intersect. Here is another example of boundary component. You can consider in complex plane. It is complex plane, and Pn is defined as Z belongs to C, such that mod Z greater or equals to N. Right? So this is another a nested sequence of subsets of complex plane such that open, connected, closure, etc. happens. Okay, so here is the next definition. Next definition is that how do you say that these any two boundary components are equivalent or not? So this definition says that two boundary components are equivalent if and only if there exists a subsequence of the first boundary component eventually contained in the second boundary component, this one, and there is another subsequence of the second nested sequence which is contained in the first one. So you can check easily that this is an equivalence relation, and after considering this equivalence relation, I will denote the equivalence class by this, and an equivalence class will be called as an end. Okay, and the space of ends, I want to give a topology on the space of ends. So this topology comes from this. So here is the topology description. First, take any subset X which has a compact boundary and consider all those ends. So it is an end. Okay, all those ends which actually eventually contain the tail. So it is a tail, and X contains eventually this tail, right, for some large n. And now consider and vary X, and consider X all possibility consider the all possibility of X. I mean, X can be any compact, any subset of sigma with compact boundary, and vary X dagger. So one can check that this is a basis, and this basis will give you a topology. Okay, and now all right, so n punctured plane has exactly n plus 1 ends, right? So let us try to see it. Suppose I have deleted 3 puncture. This is page, my page is actually R2, so I have to consider an end. So take small circle, I mean balls, and here again so this is this kind of thing, like I'm considering concentric small balls around this puncture. This is one puncture, this is another puncture, this is another puncture. So this will indeed consider okay. So here notice that open, connected, non-compact, boundary is compact, and this is obviously satisfied. So, and the other one is the infinity puncture located at infinity. So for that, I need to consider outside of this ball, right? This one, outside of that ball. So thrice punctured plane has exactly 4 ends. One end is located at here. This is one end. Another end is another here. Another end is here. And the fourth end is the infinity. Okay. Now look at the Loch Ness monster surface at the very beginning. I mentioned. Yeah, here is the Loch Ness monster surface. So it has exactly 2 ends. Sorry, Loch Ness monster has exactly 1 end starting from here. right? And it has exactly two ends. This way. Okay. So Jacob ladder surface has two ends, and Loch Ness monster has one end. Okay. And here is the definition of non-planar end. So non-planar ends means consider a boundary component. So boundary, so P1, P2 is a eventual, it is a decreasing sequence of open connected subsets such that boundary of each PN is compact and as usual defined here. Closure of each component PN is non-compact and any subset intersection, this kind of thing, what I mentioned here. Well, so we say that this we say PN is planar if each PN, if PN are homeomorphic to open subset of R2 for all large N. I mean, eventually you can embed this portion into the plane. So what is the idea? Idea is behind this that, so suppose here, here, but after that, this portion. So let's say P1 starts from here. Okay, P1 starts from here. P2 starts from here. Right? P3 starts from here. Notice that P1 is not embeddable in plane because it contains a handle. P2 is also embeddable in end. P3 embeddable in end. So an end is said to be planar if all possible, I mean, eventually it is embeddable in plane subsets. Okay, and here is a definition of the non-planar end. Non-planar end means PN is not planar. It means that it is not eventually embeddable in plane. And using the topology of, as I mentioned here, using the topology, we can produce so that this space is a closed subset of this set. Okay, and here is the abstract definition of genus. So abstract definition of genus is that take consider all compact polar surface and take their supremum of genus. You can define the genus for compact polar surface. It is a well-defined notion. As in the background section, I have defined the genus, and you need to take all supremum over all these supremum over all these genus, and this supremum is the genus of the sigma. So what is the meaning of genus? So if G of sigma is finite, let's say it is finite, then you can, so it is, what is the meaning? So it means that you can produce a compact border surface S inside sigma such that after deleting S from sigma, this is embeddable in plane, right? This is the meaning. And genus is infinite, it means you have at least one non-planar end, right? Because notice that we can't accumulate an ordinary point by handles. We in order to accumulate any point by handles, you need to have a puncture. So genus is infinity means you have at least one non-planar puncture or one non-planar end, and vice versa. If you have at least one non-planar end or not one non-planar puncture, it means your genus is infinite. Okay, so here is the main theorem. I mean, earlier I have stated deformed version, but here is the right version or correct version is Karekharto classification theorem. So it says that if you are given two non-compact surfaces, they are homomorphic if and only if their genus are the same, and there exists a homomorphism sending space of between the space of ends, sending the non-planar ends to the non-planar ends, right? And here is the theorem. It is the characterization of the space of ends. So ends comes with a topology that I have mentioned here for a subset. This one, this topology. Using this topology, one can show that ends is actually totally disconnected, second countable, compact. So in particular, ends is homeomorphic to a closed subset of the Cantor set. In other words, you can embed the space of ends into the real line, because Cantor set can be embeddable in real line. Well, so here is the Iron-Richard realization theorem. It says that if you are given two subset X and Y, X is certainly non-empty, and Y may be empty, Y may equals to X. So Y may be empty, Y may be X, possible. But X and Y both are closed subset of the Cantor set, standard Cantor set, and Y contained in X. Then there exists a non-compact subset surface, such that end space of sigma is actually X and non-planar ends is actually Y. So what I'm considering, so if you are given to closed subset so that one contained in another, then you can realize these two subset of this Cantor set by the space of ends of some surface. That is a realization theorem. Okay, so what's the idea behind the proof of realization theorem? So first delete X from H2. Say X is given. X is a closed subset of Cantor set. Closed subset of Cantor set. Right? Delete X from H2. Y is also given. Y is also given. And Y is a subset of X. Accumulate each point by handles as I defined earlier. Okay, and now so a point X gives an ends and vice versa. This is a hard part of the theory. Actually, both sides are hard. One needs to check that ends gives a puncture and puncture gives an end. Both are hard part. I'm not going to the proof, but this is a hard part. Proving. And finally, you have to show that there is the bijective correspondence. And this bijective correspondence sends this Y to the non-planar ends. So using this rough idea, what I'm showing, so I can show that given any two closed subset, one contained in another of Cantor set can be realized by a space of ends and space of non-planar ends. All right, and in case of Y equals to empty, you can just add finally many handles, no problem. It won't affect on the space of ends because we are just adding finitely many handles. Using finitely many handles, you can't accumulate a puncture. Okay, so here now we want to answer the question number 2 and question number 5. So what is the question number 2? Okay, where is the question number 2? Let us try to answer this thing. How do you define the okay, first question number 2. So closed 0, 1 interval is here. Let's say I want to show that this space has exactly one end. One end. Once I show this that this space has exactly one end, then they are homeomorphic because we have no genus, and so it means we have no non-planar ends. So we just need to show that there is exactly one end of this surface, and R2 has exactly one end because we are deleting 1 points from the sphere. And as I told you just few seconds ago, that each puncture gives you an end, and each end corresponds to a puncture. So S2 minus 1 point is S2 minus 1 point is R2, and we are deleting 1 point from the S2. So we are getting one end actually. So once I show that close 0, 1 clause 0 after deleting this subset, it has exactly one end, then we are done. So how do we show that it has exactly one end? So idea is very clear. You just need to consider this eventual sequence, decreasing sequence of open connected subset, right? So how do I construct this subset? Complement, right? Take another small subset. Let us draw in another color. Maybe this one is better. Another small one. Take the outside. Consider another color, a small one, and consider the complement. So this will produce an eventual decreasing sequence. Yeah, eventually, so inside H2, you have to consider this will produce an eventual decreasing sequence of open, connected, non-compact, one boundary component is compact, this kind of theorem. Okay, using this, you can show that it has exactly one end, and then classification theory says that R2 is homeomorphic to this one. All right, so this is the almost end of this talk. I'll just mention another theory, one statement, and then I'll stop it here. So it is the pan decomposition of non-compact surfaces. So pan decomposition means, so recall that if you are given a genus 2 surface, this surface, it has a pan decomposition. Pan decomposition, you can think it as follows, right? Here, pan decomposition. Here is another pan. Right? And if you glue these two boundary, if you glue these two boundaries, if you glue these two boundaries, you will find genus 2 surface. Right? Similarly, you can produce that so that SG or G greater or equals to 2 has a pan decomposition. Then is there any pan decomposition for non-compact surfaces? It is possible. How do I decompose using just pan? Well, so in case of non-compact surface, you can't expect that you can't expect that your non-compact surface can only decompose into pair of pans, unless very few surface, like for example, Loch Ness monster surface. It has decomposition only using pair of pans, like this one. You can start with. Okay, here. Again, here consider, so you can decompose into pair of pans. It's bad drawing. Anyway, so what's my claim? Claim is that you can decompose using only S0,3 is a pair of pans. But in case of so why it is possible? Possible is just because that this surface, I mean the Loch Ness monster surface, has exactly one end, and the end is accumulated by handles. But if your ends is not accumulated by handles, then you can't decompose into the pair of pans. For example, let's consider, let us first erase it. Okay. Like this one. This is the genus, this is the genus, and this is the puncture. This is a planar puncture. So this surface is one puncture, two genus. So you can again find out pair of pan decomposition. So the pair of pan decomposition, how does it look like? Sorry. And you need to use another pair of pans. And now you need to use one punctured disc. Okay, so I'm using three pair of pans and one punctured disc for that this surface. This is the one pair of pans decompose. So in case your surface has planar ends, you can't expect that your surface can be decomposed into only using pair of pans. This is impossible. In case of planar ends, you need to use one punctured torus. Sorry, one punctured disc. Yeah, this is the one punctured disc. All right, so here is the Goldman idea. So Goldman started with an inductive procedure. Start with a disk. This is the starting point. This is the first and the last time we are using a disk. We won't use this after this. After that, you can consider either two-hole torus, annulus, or pair of pants. And you can add inductively one by one. So I've started with this, then I add a pair of pants here, then I add one-hole torus, then I add one-hole torus, then I add annulus, pair of pants, annulus, one pair of pants, two-hole torus, so on. So if you consider all possibility of adding these types of surfaces, compact border surfaces, the limiting surface will give you the all possible non-compact surface. So here is the inductive procedure. So start with the disk. To get ki from the ki plus 1 from ki, I mean ith step, to get from I plus 1th step from the ith step, you just need to consider either this thing, annulus, or pair of pants, or two-hole torus. Consider at least 3 of the compact border surfaces, say S, and then you have to identify one boundary circle of S with one boundary circle of Ki. This is the inductive constant. So substrate disk, then I consider pair of pants. So I'll identify it with this theorem, sorry, this thing. Okay. Then I will consider genus 2 surface, right? Sorry, genus 1, two-hole torus. I'll identify this again, so on. This is the inductive procedure. So this inductive procedure says that you can construct all non-compact surface using this inductive procedure, and it is more or less clear, right, from our representation theorem. Yeah. So notice that here, why I'm drawing here, representation theorem says that any surface is obtained from deleting puncture, then adding accumulating this puncture by handles, right? So when I'm considering disk in the Goldman construction inductive procedure, this disk nothing but this portion. When I'm considering pair of pants, all right, pair of pants, then I am considering all possible number of ends. I'm considering number of ends. When I'm considering two-hole torus, I'm considering genus. And when I am considering annulus, it means I'm considering non-planar ends, right? For example, pair of pant for example, inductive construction of this surface, how does it look like? Let us draw it once. So here it has infinitely many handles and exactly 4 ends, right? So I'll start with a disk. All right. So I want to construct 4 ends. So first, then let's us draw it here. Pair of pants. Okay. Then again here, pair of pants. So 1, 2, 3, and again here another pair of pants. Okay. Now it has 4 ends. 1, 2, 3, 4. Now try to add two-hole torus every time here. Let's say two-hole torus here, two-hole torus here, two-hole torus. And here you need to add annulus. Here you need to add annulus, annulus, annulus here. But here you need to add two-hole torus from here. So using this, you can show that this corresponds to an end, non-planar end. This another corresponds to a non-planar end. This corresponds to a planar end, this one, and this corresponds to a planar end. So this is the rough idea of constructing any non-compact surface using only 4 compact border surface. And the last thing that I want to mention is that you can see there exists a graph. This graph. This consists of blue straight line and red circle. This red circle. Alpha type circle, beta type circle, gamma type circle. So one can show that there exists a deformation retract onto this graph. In other words, sigma is homotopy equivalent to countable, at most countable, sorry. So let's script alpha, and cardinality of alpha is less or equals to aleph naught. So sigma is homotopy equivalent to a countable wedge of circle. And in other words, fundamental group of any non-compact surface is free. Right. So this is almost at the end of this chapter. So I just want to mention that not every group can be realized as a fundamental group of surface. You know that for closed surface, it is a fundamental group like how does it look like? It is a free group quotient out by some kernel or normal subgroup, better to write. Normal subgroup for closed surface. And for non-compact surface, you just notice that it is free. Even if you consider non-orientable non-compact surface, then again you can show that it is fundamental group is free. So you can so not every group can be realized as a fundamental group of some surface. Yeah, and that is the end of this thing. Okay, so if you have any question or any idea or any comment, observation, you can tell me.